Welcome back friends to another tutorial in continuation to series of practical machine learning for beginners. In my previous tutorial, I talked about one of the important metrics in linear regression, which is R squared, and we saw this over an example of simple linear regression where one feature was deriving prediction of target variable sales. In this tutorial, we'll be talking about multiple linear regression where sales is driven by more than one feature and hence it is called multiple linear regression. Along with that, we will be looking at the limitations of R squared matrix, and we will be talking about new matrix called adjusted R squared, which will be overcoming these limitations. So let's head back to our notebook and get started. The link to complete machine learning series and to the dataset used in this tutorial is provided in the description below. So friends, I have already imported the libraries which we will be requiring in this tutorial: pandas, matplotlib, seaborn, and sklearn library like linear regression, print as a split, and some of the important metrics. We have uploaded the dataset advert_csv, and as we can see with the help of df.head the first 5 rows of the dataset. Let's have a quick look at the information of this dataset. df.info, which will give us a summary of this dataset in terms of the total number of records available, and also for each column how many values are available. So we can clearly see that there are 4572 records while the number of records available for feature are less. What that means is there are null values in the record, and we will not dig deep into this, although we can see df.isNull with the help of this, that how many null values are available for each variable, and it shows that TV has 10 missing values. While I'll be talking in detail about null values and how to explore, how to handle in one of the upcoming tutorial, right now what we have simply to do is to drop these values. And why? Because when we will go for machine learning modeling, it will give us the error. Simply machine learning model cannot handle missing data, and this is one of the data pre-processing step. Though this is not the way to straightforward handle the data, just to drop the missing values is not the right way, but right now we will be going for that because the focus is different. Right now we will simply drop using drop NA, and let's see the information again. df.isNull, we can again give isNull.sum to check out how many missing values are there after doing drop NA, and we can see there are 0 values. And if you do df.info, right, so if you do df.info again, you will see that 4546 records are present in total. That means we have dropped the delta of 4572 and 4546 as part of dropping null values. Let's have a quick look on the relation between each of the variable. Now the important thing here to note as part of multiple linear regression is this time sales revenue is driven by 3 variables, 3 features: TV, radio, social media, budget. If you have a look at this data set, right, so TV has certain budget, radio has certain budget, social media has certain budget, and then we have a sales revenue, right? So let's say there is a marketing campaign and we invest in each of these channels and we get the sales revenue, and we are wondering what is useful, which channel is useful, how much the sales revenue is impacted by each channel, who is contributing most and who is contributing least, right? So the first thing is to explore the data through visualization. Right now we have been using scatter plots to do the same, and individually we can plot the scatter plot, or we will be looking at something new which is called SNS Pairplot, which at one go gives the relation of that variable with the target variable. And how we can do that, and what we have to do over here is df which is a data frame, and we have to give 2 more argument, xvars equal to, and the list of the columns which we want to see as part of x-axis. So we will just see the output in some time and we'll see how it appears. So we want to see the relation of these variables, right, with respect to sales. We will give these variables which are features or independent variables, and we'll give dependent variable over here. Let's run it. Again, this is a scatter plot, but we are able to create it in one go. Instead of creating 3 scatter plots, it has created one target variable on the y-axis. If we have a closer look at these scatter plots, we can see that there is completely almost linear relationship between sales and TV. So more the budget you fed in TV in market campaign, the more the sales is. While radio is less linearly related to sales, right? Some of the values, even we are increasing the budget, they stay in the same zone of sales. Again, social media is kind of linearly related, but the relationship is not that linear. Even on increasing social media budget, sales stays the same, right? So if you see these data points, right, here the sales remains the same, even the budget is more for social media. So it is not contributing that much to sales like the TV is, right? And so here in this multilinear regression, where we are talking about more features, right, more than one features, what we can conclude is that all the features are not contributing equally. One feature is more important than others. We can also visualize the relationship between various features along with the relationship between target variable and feature, numerical features, using a map called correlation heat map. And let's first see how it works. So we can create a variable correlation equal to df dot core. Then we can print correlations and see what information we have obtained using this core method of data frame. And as you can see, it gives us some values. What are these values actually? If you see, radio is related to TV with 0.86, right? What is that relationship? We will talk about it, but let's just talk about the relationship of TV with sales, radio with sales, and social media with sales, right? And we will see that TV is highly related to sales. So what are these values actually? These values are called correlation coefficients, and they range from -1 to +1 and indicate whether there is a positive correlation between a variable or a negative, and 0 indicates that there is no. If it is negative, that it means that with the increase in one, other decreases. Since it is positive, we can say that when the TV budget increases, sales increases. Information we can visualize with the help of heat map. And how we can draw that? Using SNS.heatmap. And we can pass this correlation. Let's see what we get. We get this. As we can see the scale, that the lighter the value, it means that more is the correlation, right? And lower the value, it implies that lesser is the correlation between those variables, sales, TV, radio, TV, sales, and so on. We can also visualize the relationship between the features amongst themselves, and we will be using this for very important concept called collinearity when we will be doing data processing. But effectively this plot is used for identifying the most relevant features during feature selection process. We can also see the values of correlation coefficient using annote is equal to true. There it gives you the relationship. We can customize it for various themes, various color palettes using CMap and more arguments. But if we have a look at sales and TV, we can clearly see that sales is related to TV in a perfect relationship, which we have seen. Sales, of course, will be related to sales with one relation, right? With radio, we can see that the relationship coefficient is 0.87, while with social media is 0.53. So this indicates that with the help of this, we come to know that TV is the most important feature driving sales, while radio is lesser important and social media is the least important feature which is contributing to sales over here. It's time to do ML modeling, and we will start by splitting it into target and feature. X will contain the features and we can obtain it through df. And this time what we will do, we will just pass the list of the columns which we want. Earlier we were just dropping the target variable. So there are various ways. Right now I'll just do in this way, where I can pass a list of the columns which I want in feature. Or what I can do, I can also have this list as predictors, all right, and pass this list over here. I can obtain the target variable using df sales. Let's have a look at some of the values in X data frame, and it gives us all the features: TV, radio, social media. In case we want to have few features from this list, we can always slice the list, and we can pass the index from which we want the variable. Let's say TV has index 0, radio has 1, social media has 2 index, and let's say we want only TV and radio, we can pass 0 to 3, right? More than the index which we want. So if we run this now, for radio index is 1, so we will pass 0 to 2. We can fetch limited number of features from this list. All right, all good so far. For now, let's just fetch all the features, and let's also split the data into train test split data set. Let's run this, and now let's create a model. We will create the instance of linear regression model, and we'll fit the data to it. We'll fit the training data to it. With the help of values between features and the target variable, model.build will drive the relationship between the features and the target variable, and since it is linear regression, it will derive the linear relationship. Then we can predict the value y_pred is equal to, using model.predict, where we'll just use x_test, the unseen data for the model. So we have a prediction. And now is the time for performance evaluation of this model, and we'll just, for time now, we will use only R squared matrix which we learned in our previous lecture. For R2 we can have R2_score. We have already imported these matrix libraries. Can pass y_test, y_pred, and let's print the value of R2. Okay, so this is such a high amount of R2, right? Because we included TV, it was almost linearly related to target variables, and we can visualize the difference between residuals between y predicted and test. Let's do that as well. To visualize the values, I have just copy pasted this code where I am drawing the scatter plot between y test and y predicted with the labels. Then I am also drawing the relationship red line to indicate the y test values. So let's run it. As you can see, why this is so blue, because there are so many data points, right? Let's just reduce the number of data points first. And what I can do, instead of taking this whole data set, I can take the subset, let's say subset of this data frame. This is just for the sake of visualization so that we understand it well. df dot, and we can use ilog, and we can pass the number of records we want from 0 to, let's say, 200, and we want all the columns, so I'll just give colon over here. Let's run it all. And before that, here where we are predicting the values, right, where we are splitting the data, instead of df I can pass subset_df. We are just doing for just reducing the number of points so that we can visualize and understand well. And let's run it all. So as you can see, this predicted line, this red line, and this actual points are fitting very well into this data. Of course, we can see the R2 score was also high. This is when all the features are included, and let's see the effect when we include only one feature. Let's say we include, of course, for TV we will get a very nice fitting line. So I will just pass, let's say we pass only this social media. All right, so if I run this over here, so feature is only social media. At that time, what will happen to R2 score? Let's see. And we can see that R2 score has decreased drastically, right? From 0.99 to 0.37 if we are only including social media. And we can also see this best fit line is not fitting that well to all the actual points, and there is lot of residual. Sum of residual squares is quite high, and we already discussed about this. R squared matrix indicates how well the points are fitting with the best predicted line, but there is a caveat here that with the if we take only TV, okay, radio, let's say, and if we don't take social media, what will happen to our score in that case? What we are discussing is what will happen if we are adding more and more features, and some of them are not as good, or some of them are not important, right? Social media still here has 0.5 correlation, right? Still it is impacting the sale, but when you will work with the very large data sets with quite a large number of features, you will realize that many features are very meekly related to the target variable, and we are just adding them. And what is happening with R squared when we are adding more and more variables, what is happening to it? And still is the R squared a good indicator to show that the model is good, right? So let's do one thing, okay? I will not create the code over here completely just for the sake of time interest. What I'll do, I'll just copy paste the code of for loop where I will pass the number of predictors one by one. Okay, first I will pick one predictor, then two predictor, three predictor, and then we will see the effect on R squared with that. Okay, so let me do that. Alright, so I'm here. I have commented out the previous code and moved the code over here in the for loop in order to take different number of predictors or features one by one, and all the features I have stored in predictors list. Then I have a list to score R squared values for varied number of predictors, and also I have added adjusted R squared value list, which I will be talking shortly over here. Okay, so what we are doing in this for loop, we are as we run the for loop, first we are taking only one predictor, then second predictor, then all the three predictors. All right, and I'm also using the subset like which we did, and then I'm splitting the data, creating the model, predicting the values. So eventually we are creating three models over here with one predictor, two predictor, and three predictor consequently. And then what we are doing, we are calculating the R squared value like we did earlier, and I'm also calculating one matrix which is called adjusted R square, and I'll be explaining how we are calculating it shortly. And then I am also plotting the figure which we just did, right, for each of the number of predictors. Okay, and if I run this, what we will get is this. So we have three graphs, three visualization for each model. Model 1 where I'm using just radio predictor, okay, and I can see the variance over here. Again, this second predictor where I have radio TV, I have included a very significant feature, and of course because of that significant feature, my residual square sum of this becomes less. And because of TV with social media, what is the effect? There is no effect, right? And we can see the values of R squared when we included radio, it was this, and of course with the inclusion of television it jumped drastically, right? And if you have a look at this, right, when I included this social media, which was a very insignificant feature, still my R squared jumped, right? Still my R square jumped, of course, because social media is also explaining the variance. There is a matrix which we are coming up with. This is adjusted R square matrix. If we have a close look at this, with the addition of significant feature, this adjusted R square is also increasing like R square. But with the addition of insignificant feature, this R squared is decreasing, right? And if we would have added very insignificant feature, this would have reduced drastically, while this R squared would have increased. So coming back to square one, R square alone is higher, the R square alone is not the right judgment indicator for the goodness of model, what we need is our adjusted R square, which is the matrix which takes into consideration number of predictors which we are adding and how significant those predictors are to the model. All right, and how it is calculated, let's see. So let's have a look at the formula which we are using for adjusted R square. To calculate adjusted R square, we are using this part of code, which is effectively using this formula. Adjusted R square is equal to 1 minus R squared, right, into n minus 1 divided by n minus p minus 1. Have a closer look how we are deriving n and p over here. N is referring to the total number of records, while p is referring to the number of predictors. Let's see how we are arriving at this formula. We know from our previous tutorial that R squared is given by explained variation upon total variation, which we derived from sum of the difference of sum of total variation minus unexplained variation, which was sum of residual squares, right, divided by total variation, which was again sum of total variation, which this we can write it as 1 minus SSRES, sum of squared residuals. Again, to indicate with the help of line, let's say this is our best fit line and these are our actual points. So this is the residual, right, and SSRES is the sum of all these residuals and squaring them, while total variation was when we draw a mean line for these data points, the difference is the sum of the variation of all the points, right. So this is how we arrived at R squared. You can go through my previous tutorial in case you want to know more. Now the problem which we saw with the R squared is that it tends to increase with the addition of more predictors. So adjusted R square, what it is doing, it is modifying R squared to account for the number of predictors, right. So we have number of predictors like TV, radio and social media, and we also had just predictor as TV, radio, and here R squared was increasing. So adjusted R squared, what it is doing, it is considering degrees of freedom. Okay, so it is dividing this by total degrees of freedom. Okay, now what is degree of freedom? You need to go to my first tutorial about statistics. This is what we are doing. Effectively, we are arriving at this formula for adjusted R square. 1 minus R square n minus 1 divided by n minus p minus 1, where n is the total number of records or observation and p is the number of predictors. Now we saw that as we added social media, right, which was least significant variable, our adjusted R squared decreased, but R squared kept on increasing, right. So adjusted R squared is basically decreasing when we are adding irrelevant predictors to the model, as it is accounting for the number of prediction. And this penalization helps to prevent something called overfitting, which we will be talking in detail in one of the upcoming lectures. Of course, it is a better matrix than R squared, especially when we are going for model comparison and model selection. We had three models over here, model 1, model 2, model 3, and we can clearly see that model 2, which has radio and TV as a predictor, can be the better model to be chosen here, and we can ignore social media as a predictor, right. So that was all about adjusted R squared, and with this I have completed all the primary metrics which we used in linear regression, including mean squared error, root mean squared error, mean absolute error, r squared, and adjusted r squared. So far what we have done is I have introduced you to classification problem in machine learning, regression problem, and we dive deep how regression works, and we also dive deep into different performance evaluation metrics. We have also got an idea how machine learning modeling works, although it involves many more steps. Now what we will be doing with this knowledge base, we will be working on one regression problem in our next tutorial. Before we go to next concepts in machine learning modeling,